this book, got excited for 5 minutes, and then closed it, thinking I'll try it later. I've done that many times, but this time we are doing it differently. We'll be actually finishing it. So, the first chapter, the role of algorithms in computing. Let's start. While I'm reading, you can read yours, and I'll get back to you when we have to start solving exercises. So, yeah, it's a reading time. Let's go. first question is describe your own real world example that requires shorting and describe one that requires finding the shortest path between the 2 points. Okay, this seems fairly easy. So we have to say one example where shorting is required and one example where we use the shortest path. Okay, shorting. So let's say if like there are teachers, they maintain register of students or even the attendance where the files of the students are like in shorted order. It's easier for them to access. Also the attendance of students happen and like the names of the students are shorted. So that is one example for shorting. And the shortest path algorithm would be that I use on daily basis would be like I want to reach my home as soon as possible from office. So yes, this is my office. Okay. Yes. Okay, it looks more like CPU, but yeah, manage. Still looks like CPU. Okay. Yeah, so shortest path is where I have to reach from office to my home is where I would be using the shortest path algorithm. Now next question is, other than speed, what other measure of efficiency might you need to consider in a real world setting? So they're asking what is the other measure of efficiency that I can think of. So one measure of efficiency is speed, and the another that I can think of is the amount of effort that is required. So one thing is how fast a person is doing a work. And let's say if there is a task, how many people are there to do that work, right? So that would be the amount of effort or amount of people required to do a work. Or like we could also say the amount of memory is required. Okay, next is select a data structure that you have seen and discuss its strength and limitations. Okay, since I was a computer science student, so array is one data structure, very simple data structure, and its strength is that we can access the element in it in constant time. So big of one is nothing but in constant time, and its limitation is that it has static size, like it does not have dynamic sizing. So let's say if I've created an array of size 10, then I will not be able to increase its size to 11. Now if I want to insert an 11th element, it would not be possible in array. Yes, so that it's its limitation. Now coming to the fourth question, how are the shortest path and traveling salesman problems given above are similar and how are they different? Okay, so we have shortest path and we have traveling salesman. Okay, one thing, okay, they're similar because we have to minimize the distance. I mean, in shortest path also we try to minimize the distance. And how are they different? Okay, so shortest path is like trying to minimize the distance between the 2 points, and traveling salesman is trying to minimize the overall distance. Okay, so what I can think is this is point A and this is point B, and if this is point A, there are point A, B, C, D. Now shortest path is just me going from A to B, whereas traveling salesman is me going from E to B, B to D, D to C, and then C to A. Okay, so what I'll try to do is I'll try to minimize the overall distance. This, I mean, here I have obviously, if I would have chosen A to B, B to C, C to D, and D to A, the distance would have been lesser and it would have been a better traveling salesman it would have been a better answer for the problem. But yes, I guess that's the difference between this. Probably I have not articulated in best manner, but overall essence, I guess this is it. Now, fifth one. Suggest a real world problem in which only the best solution will do, and come up with one in which approximately best solution is good enough. Okay, I don't know why I'm so stuck to shortest path algorithm, but yeah. Shortest path algorithm is, I guess, where approximately best solution would do, because if I'm reaching my home 5 minutes later, I would not have any issue. I guess it's fine. And the one where apparently only the best solution would do is is okay, yeah, would be let's say there are airplanes and they travel in their defined trajectory and their route is decided on the basis of some algorithm. Now, if the algorithm is not giving the best solution, then there can happen lots of collisions. They will collide with each other, and which will cost lots of lives, which are there in the plane. So I guess this is one example where only the best solution would do. Now, next question. Describe a real world problem in which sometimes an entire input is available before you need to solve the problem, but the other times input is not entirely available in advance and arrives over time. Okay, so shorting is one problem where we have the entire output given at once. Let's say it's 11, 12, 17, whoopsie, 59. And like we have the entire input available and then we try to short it. So we have all the input present at once in the very starting. Now next would be where it is not available. Okay, so one example they have given is of the hospital. Like obviously in the very starting of the day we do not have all the patients. They arrive over a certain period of time and the allocation is done accordingly. So yes, hospital is this one example, hospital. And also these are called online algorithms, so we'll just write that hospital. In hospitals we use this so in hospitals we have this online algorithm where the input arrives over the time and it's not present in the very advance. Okay, so that's it for first part. Now we'll start studying the second part, which is algorithm as technology, and once we are done reading it, we'll come back and we'll solve the next questions. Till then, let's start reading it. So the first question is, give an example of an application that requires algorithmic content at application level and discuss the functions of algorithms involved. Okay, one thing that pops up in my head instantly after reading the question is that any application where we have to navigate or is navigation based would be requiring to use algorithm at application level. So let's say there is Google Maps. I don't know why am I writing spelling of it wrong. Yeah. So there is Google Map and like any other map based application would be using the algorithm content at its application level. Now second question is, suppose that for inputs of size n on a particular computer, insertion sort runs in 8 n square steps and merge sort runs in 64 n log n. For which values of n does insertion sort beats merge sort? That means rate of n squared should be less than 64 n log n, and we have to find all such values. Okay, so now okay, this n gets cancelled. Let me use different pen. This will be 8, and so we basically have to find for which values of n is less than 8 log n. Okay. Okay, so basically since it's merge, since it is merge sort algorithm, this is nothing but 8 log 2 of n, and to calculate that in my calculator, what I can do is that I can have, because in this we only have with a base of 10, right? So log L it is, guys. Okay, yeah, so we could start putting the values of n for which it satisfies. We could start with 50 is 50 less than divided by which means is 50 less than 8. Okay, first I'll do log 50 divided by log 2. Now that's 5.64, so multiply by 8. Okay, so for this one it does not suffice. That means like probably we could have below 49 all the values would suffice. Let's take 45. N is equals to 45 is 45 divided by log of 2, which would be equal to 45 less than what it is, log of 45 divided by log 2 multiply by 8. So it is 43.94. Okay, so this also does not suffice. Let's take n is equals to 40 is 40 less than 40 divided by, which would be 40 less than log of divided by log 2, 5.32 multiplied by 8. So it is 42.575. Okay, so this one suffice. Now it could be that 41, 42, 43 or 44 suffice. So let's check till where it is applicable. So we'll try the next value. So this we tried 40 and 45 does not suffice, 40 suffice. Let's try 44. So we'll have n is equals to 44, and is my 44 less than log is 10 of 44 divided by base 10 of 2, so which is nothing but log 44 divided by log 2, say 5 point something into 8. Okay, so something that is implies is 44 less than 43. No, it is not. Okay, we'll try for n is equals to 43 is 43 less than 8. Which implies log of 43 divided by log of 2 multiply by 8. So is 43 less than 43.41. Okay, so if we disregard these decimal values, so if we take all the values from n starting to 2, okay, so n suffice for all the values which are starting and greater than 2 and less than 24, because this is pretty much, I mean, yeah, this is not considering decimal. That is why I'm like kind of calculating it this way, but obviously we could calculate n is equals to 42 as well. Okay, so there is that. Now coming to next question. So question number 3rd. Coming to next question. Question number 3rd is, what is the smallest value of n such that an algorithm whose running at time 100 n square runs faster than the algorithm whose running time is 2n. Okay, on same machine. Okay. So basically what I was trying to think is, instead of like putting random values of and trying to solve it, if there is another manner I could do it. basically I could solve it more, but then again I'll have to solve the logs if I try to take log on both the sides. Okay, what I could do instead is, for now I'll put random values, and please if someone has like better way, then obviously trial and error is not the better way, but also I don't want to like get stuck in logs. Yeah, if there is just any other method, please ping down in the comment section. I'll start with 10. So 10 square is again nothing but 100. Is it less than 2 to the power of 10? Now again for this I'm using only calculator, but 2 to the power of 10 I kind of knew. So is this less than this? Definitely not. This was for n is equals to 10. Let's try for n is equals to 20. So we kind of know it would be this. No, it will be 4 actually. 2 to the 4. So 2 to the power of 20, that I'm gonna calculate using calculator. 2 to the power of 20 is 1048576. I guess. Okay, so this is not less. I mean, this is less, sorry. I was meaning that is not less, but yeah. This is less, so we might have a value in between. Let's try with 15. N is equals to 15. I know 15 square is 225, but still. 22500, is it less than 2 to the power of 15? 22500, is it less than 15? Let me just see. 2 to the power of 15 is nothing but 3, 2, 7, 6, 8. And yes, this also suffices. So we have to find this runs shorter. Yes, this is equals for n is equals to 15 also. Let's 10, it was not sufficing. 15, it was sufficing. Let's do 14. Okay, 14 square is 496, but let me see. I remember it's 196. I always get confused just for this one. And 2 to the power of 14, so is 19600. Is it less than 2 to the power of 14? It is nothing but 16,384, and it is not less than that. Okay, so the first value, like the value of n for which 100 into n square is faster is 15. So any input which we have, like starting from n, okay, I'm gonna conclude it in better manner. So for all the values of n greater than or equal to 15, we will have 100 n square running faster than the. With this, we complete the second. Okay, so now we are at a stage that we will be solving the main problem of chapter number 1, which is comparison of running times. For each function f of n and time t in the following table, determine the largest size n of a problem that can be solved in time t. Assuming that The algorithm to solve the problems takes f of n microseconds. Okay, so the first problem basically says algorithm which is f of n takes t microseconds time, and we have to find the maximum input size that could be solved in like given time intervals. First we'll solve for 1 second. Okay, now the f of n first given is log of n. Now we know 1 second is nothing but 10 to the power of 6 microsecond. If we just keep n here and take log the other side, it will become 2 10 to the power of 6, 2 to the power of 10 to the power of 6. Now if we have to do that for 1 minute, it would be log of n in now in 1 minute we have 60 seconds and 10 to the power of 6 microseconds, so it will be 2 into 6 into 10 to the power of 7. Now for 1 hour it will be log of n, like it has 3600 seconds into 10 to the power of 6, so n is nothing but okay, yep, so I had written in 1 hour we have 3600 seconds, and then n would be nothing but 2 to the power of 36 into 10 to the power of 8. You can also write it in 3.6 into 10 to the power of 9. Now in 1 day we have 24 hours. Log of n. Each hour has this much time, so our n would be, let me just multiply and see, 24 into 36, which is nothing but 864. So it will be 2 to the power of 864 10 to the power of 9. I can also write 10 to the power of 8. Yes, that would be in 1 day. Then 1 month, we'll take that each month has 30 days. So 30 into 24 into 3600 into 10 to the power of 6, where n would be 2 to the power of, I'll just multiply 864 into 3, which is nothing but 2592, multiply by 10 to the power of 9. Yeah. Then in 1 year, it should be pretty easy. It will be just multiplied by 12. 2592 multiply by 12. Yes, now if you're like taking like for 365 days, you can have like different computation. Yeah, so if you do by the day or if you do by the 12 months, it would be different. So we could do by day. So in that case, you'll just multiply 864 into 365, which will be 31536 360 into 10 to the power of 8. It could be 9, 10, 11, 12, 13. If you want to write, you can write 2 to the power of 3.15 and 10 to the power of 13. It would be at that time. Now for 1 century, century is nothing but this would be all of this is in power, like Probably it's not coming in handwriting. I'll try to make it more proper. So yeah, 315,360 into 10 to the power of 9, 10. Yes. Okay, yep. So for log of n, this would be the size of inputs which could be solved in 1 second, 1 minute, 1 hour, a day, a month, a year, and a century. Now we'll move on to the second row. So the second row is row 10. So first we'll solve for 1 second as usual. Row 10 takes 10 to the power of 6 microsecond. So n would be 10 to the power of 12. We are squaring on both the sides. And then let's say in 1 minute, 1 minute has 60 seconds. Again 10 to the power of 6. And would be 6 6 36. Double 0, it would be 6. Oh, we're squaring both the sides, so 12, 13, 14. Then 1 hour. In 1 hour we have 3600 seconds. 10 to the power of 6 again. Let me just get the square of 36. 36 into 36 is 1296. 1296. 12, 13, 14, 15, 16 it would be. So you can like get like 17, 18, 19. You can write it as 1.29. That is better method of writing. Just because I'm trying to avoid decimal here, I'm writing it in this manner. Okay, now 1 year done, 1 hour done, then a day. A day has 24 hours. And 3600 to the power of 6 and would be let me just do this, 24 into 3600 into 10 to the power of 6. Square of answer is nothing but 7.46 into 10 to the power of 21. That is for a day. Now for 1 month, 10 root and okay, 1 month has I will take 30 days for now, like we had taken in the last one. 24, 3600, 6. Now n would be equal to, okay, because I'm doing this calculation in calculator, it looks very easy, like I'm just putting straight away digits and multiplying it to the power of 6. I've got an answer. I'll square the answer and I'll get it as 6.71 to 10 to the power of 24. Now an year has 365 days and 12 months, like so we'll do it according to the days. 365 into 24 600 and would be 365 into 24 into 3600 into 10 to the power of 6. Answer I've gotten. Square of it would be 9.945 into power of 26. Now 1 century. Whatever current for year, I'm just going to multiply it by 100. Into 365 into 24 into 3600 into 10 to the power of 6. Square of that is nothing but 9.94. 10 to the power of 30. Yeah. Also, another way to do is to like just take the time and like keep squaring it on the top of days, or like by whatever factor n is increasing by the same factor. If we increase the time, we will be able to get the answer. Okay, so for an algorithm which requires square root of n time to solve, these are the sizes that could be processed in a second, in a minute, in an hour, a day, a month, a year, and a century. Moving on to the next, which is third one. And so now this is pretty straightforward, right? Here, since time is increasing linearly, so let's say if 1 second is taking like 10 to the power of 6 is the maximum input size, in 1 minute it will be nothing but, in a minute we have 60 seconds, so same. And then in an hour we have 3600 seconds, so that would be it. In a day we have 24 into 3600 seconds, so that would be it. In a month, taking 30 days we have, so 30 into 24 into 3600. This again, for a year you could choose to go by day, that is more appropriate. 365 into 24 into 3600 and the power of 6. And in 1 century, whatever we have in a year, just multiply it by 100. So 24 into 3600 into 10 to the power of, yeah. So these would be our answer for the algorithm, which is like linear algorithm, whose like input size will be increasing by this much for 1 second and for 1 hour, minute, and a day, month, year, and a century. So now coming to the fourth one. And login. Okay, I'm not gonna start with one. We could just try to like search for the mid values. I could try with 50,000. And again here the log, I have calculated that, so log of 50,000 divided by log of 2 multiply by 50,000 equals 780,482 is it less than 10 to the power 6. Okay. So yes, it is less than 10 to the power of 6. So I could try for a higher value, let's say 70k. 70k log of 70k into 10 to the power of 6, and which would be around, let me just see, log of 70,000 divided by log of 2, let's multiply by 70,000 equals to 1126654.71. Is it less than that? No, it is not less than that. So n value which could be processed should lie between these two. So if we just take average of 50 plus 70 divided by 2, okay, we'll get 60. Yeah, that was so obvious. Why did I even calculate that? But yes. Okay. So 60,000 log 2,000 less than this. Okay. Log 60,000. Sorry. 60,000 divided by log 2 into 60,000. It is 95236 and 10 to the power of 6. Yes, it is less than that. Okay, so that means it has to be a value above it. Now between 60 to 65 we could take, okay, I don't know why I'm obsessing with the pen color so much, but yeah, 65,000 log 65k less than 10 to the power of 6 log of 65,000 divided by log 2 multiply by 65,000. Okay, I guess that extra 0. Yes, it is 1039229.886. I will visit less than this. You see, no, it is not. Okay, next the mid of this would be 62.5. Okay, so now 62500 log 62500, is it less than 10 to the power of 6? Let us see. 62500 divided by log 2 multiply by 62500 equals 995,723 point something. Is it less than that? Yes, it is less than that. Nice. Now that means we have a value between 62.5 to this. Okay, let's try 633. Oopsie doopsie. So 63,000 log of 63,000 is it less than 10 to the power of 6? Log of 63,000 divided by log of 2 multiply by 60 take 2 3. It is 104. 4413. Is it less than this? Oh my god, such a minor gap. No, it's not. So we have a value like between 62.5 to 63. Okay, let's try 62.7. That somewhere falls in between. Okay, 62700 log of 62700 less than 10 to the power of 6. Okay, log of 62700 divided by log of 2 multiply by 62700. Oh, okay, 999,198.34. Is it less than this? Yes, it is. Nice, but we still cannot say. We have to check 62.8 so that, because if it is less than that, then we will have to again check. 62800 log 62800, is it less than 10 to the power of 6? So we'll see log of 62,800 divided by log 2 multiply by 62,800. It is 100,936. That is 100,936.352. And is it less than this? No, it is not. Awesome. So that means our answer for this is 62,700. Okay, yeah, so that's a size that we can like take for n log n. And okay, so we had solved for n log n. For 1 second, you saw the amount of computation it is required to do for n log n. So yeah, I've solved for 1 second, and similarly, we can solve for 1 minute, 1 hour, 1 day, 1 month, and a year, and a century. Okay, so if you want me to do the rest of the competitions as well, please comment down below. Probably we could do a live. Okay, I don't have audience for live, but still, if you want me to solve it, I'll probably upload another video solving step by step for the rest of the time frames. Okay, now let's move on to the next one, which is n square. Okay, so first we'll do for 1 second. Now n square takes 10 to the power of 6 microseconds. So n, it will, like in 1 second, it will process 10 to the power of 3 records. In 1 minute, if n square is this, now we know we have like in 1 minute 60 seconds, and now n would be, I'm gonna be using calculator, like it's so pretty handy. I don't know, I would have been crying like the last one I did, and I was almost crying solving it in my head. Yeah, I haven't loved calculator more in my life than today, and I mean it. So Here the size is 7745.96. We could just take it 7745. The size that can go in 1 hour would be n squared less than or equal to 3600 10 to the power of 6, and would be nothing but the square root of it. So there we go, square root of 3600 multiplied by 10 to the power of 6, and it would be 3 4, it is 60,000. Now for a day, n square, in a day we have 24 hours. 24 3600 multiplied by 10 to the power of 6, n is equals to square root of 24 into 3600 multiplied by 10 to the power of 6 equals awesome 293,938.76. So yeah, we can just take the first digits. Now 1 day, 1 month, like we have made the assumptions that we are gonna take 30 days. So n square will be 30 into 24 into 360. Now n would be square root of 30 into 24 into 3600 into 10 to the power of 6. It will be 160,996.8.944. Again we can take the first. Now in 1 year, again taking like 30 into 12, it will be losing on days. So we'll pick it up from days and we'll do 365 into 24 into 3600 into 10 to the power of 6. So n would be square root of 365 into 24 into 3600 into 10 to the power of 6, and it is 5615692.299. Again we can take the first half. And for a century, 365 into 24 into 36 7 8 9 10. So n would be 365 into 24 into 36 into 10 to the power of 10, and there we go. It would be 56156,922.99. We can take the first half. Okay. So for n square, we can, the amount or the size of the input goes up to, like, for 1 second it will be 1000, for 1 minute, for 1 hour it will be 60,000, for 1 day, for 1 month, for a year, and for a century. Now what you can see, right, like over the time, like when like algorithm's time complexity was n, it was able to take like more input size. When its complexity increased to n square, it is taking, like, we are able to process less number of data because obviously it's taking more time to process. Now coming to the next question, which is n cube. Coming to the next question, which is n cube. So first again we'll solve for 1 second. N cube 10 to the power of 6 seconds and would be 100. Yeah, in 1 minute. N cube 60 seconds 10 to the power of 6. Now we gotta do cube root of 16 to 10 to the power of 6, and it is nothing but 160 seconds. So in the power of 6. Okay. Oh guys, cube root is an issue. Okay, I have an idea. So let's do bracket 6 into 10 to the power of 6, bracket close, to the power of 1 by 3, and there we go. And it's nothing but 391 for 1 hour. And cube is nothing but, in 1 hour we have these many to the power of 6. All I would be doing is going inside and changing the first number 3600 to the power of 6. Cube root would be 1532. Okay, that is for 1 hour. In 1 day we have 24 hours. Each hour has 3600 seconds 10 to the power of 6, and then we will be just doing it cube root of this thingy, and it should be equal to 4420. Awesome. 1 day done. 1 month. Again 30 days in month. And cube 30 into 24 into 600 into 10 to the power of 6. And is nothing but into 30. So it is nothing but 13736.57. We can take starting half once again. Again 1 year we will be doing on day 365 into 24 into 3600 into 10 to the power 6. So this would be 31593. Awesome. It is obviously 0.82 something, but yes, we are not considering decimals. In century, 365 into 24 into 36, 7, 8, 9, 10, and would be 146645.54 something. Okay, nice. So these are the values for 1 cube. 100, 391, 1532, 4420, this, and then this. Now let's move to the next one. 7th one. 2 to the power of n. We'll solve for 1 second. first, as always, 2 to the power of 1. Take Okay, so now 2 to the power of n takes 10 to the power of 6 seconds. So now 10 will be log of log of 10 to the power of 6 log these two, obviously, because it has gone like that, which will eventually turn out to be 6 this. Log 10 is log 10 divided by log 2 3.32 multiplied by 6. So this here n would be 19.93. Just for 1 second. For 1 minute, 2 to the power of n, 60 into 10 to the power of 6. Oh my god. Which is nothing but 6 into 10 to the power of 7. And would be log base 2. 6 into 10 to the power of 7. Okay, let's do it. Log of 6 into 10 to the power of 7, and obviously I got to divide it by log 2 will be 25.83. 25.83 can take it 28 or like can take it 25 or 26. Okay. Now 1 hour. 1 hour has these many seconds to the power of 6, which is approximately 36 into 10 to the power of 8. N is log of 36 into 10 to the power of 8. Let me do it. And the answer is 31. Okay, why does it look like another laptop is also here? Why does it look like 37? It is 31. 1 hour and then 1 day. 2 to the power of n equals, in a day we have 24 hours. 36, 10 to the power of 8. 10 equals, I'm not gonna write it just because it is consuming space. So I'm gonna solve it. Log of 24 into 36 into 10 to the power of 8, and it should give me 36.33, which it gave. Now 1 day done. 1 month. 1 month will take how many days? Will take 30 days. So it will be 24 into 30 into 36 into 8, and will be log of this, which is 24 into 36. Okay, and it gives me 41. Now 1 year, like I said, we will be doing on the day basis, not on the year basis. In a year we have 365 days into 24 into 36 into 10 to the power of 8. Now n is equals to 44 24 365 36. Okay, it gives me 44. Okay, a century. Awesome. 365 into 24 into 36 into 10 to the power of 10. And what would be log of this? It is 51.48. Awesome. Okay, so the amount of data, or like the amount of inputs that can be done, like can be solved in 1 second, is 19, 25, 31, 36, 41, yeah, 44 and 51. Okay, now you see how drastically it has decreased from the last values where we were able to solve like in thousands, and before that in millions altogether. And for the algorithm which takes 2 to the power of n time, we are only able to solve like so little of data, like just 50 like 50 input size, like for like it will take like a century just for the input size of 50. So yeah, that is why a good algorithm, efficient algorithms are required. Now, without doing any more buck, let's move to the next and the last question. N factorial. Okay, so now n factorial will solve for 1 second. Now my n factorial should be less than 10 to the power of 6. Okay. Now factorials, we don't have n. Okay. Again, this is gonna be like the n log, and like I'll have to guess the values of n and see which one suits. Like for real. Okay. So let's say let's say 10 factorial. 10 into 9 into 8 into 7 into 6. So 9, okay, 10 factorial is 36288800. Oh, okay, this is greater than, so obviously this does not suffice. Let's take 9 factorial then. Oh, nice, I thought that 10 might work. Oopsie. Now 9 factorial, I got 362880, and yes, it is less than 10 to the power of 6. Okay, so for n factorial in 1 second, we can only have the input size of 9. Okay, now n for 1 minute. 1 minute has 60 seconds, and 60 seconds into this. Okay, yeah, which is nothing but, let's write it, 10 to the power of 7. Okay, 10 was, okay, 1 2 3 4 5 6 7. Okay, yeah, so 10 suffice. Let's do it like 10 factorial. 10 factorial is less than that. So that means 11 can also work. 11 factorial is nothing but 399,168,000. 1 2 3 4 5 6 7. Again 6, so this suffice, but that means 12 can also suffice. So let me check for 12 factorial. 12 factorial is 479001600. 1 2 3 4 5 6 7. Okay, nice, awesome. This does not suffice. That means for 1 minute we have the value of n as 11. Okay, 1 minute done. Now coming to 1 hour. Okay, 1 hour is again 3600. I'll just say 7 8 36 into the power of 8. Okay, yeah, so we have 12 factorial, which is like 1 2 3 4 5 6 7 8. Nice, here somewhere. So I can check for the 13 factorial and see what is it. And 2 13 factorial is 6 2 2 7 0 2 0 8 0 0 1 2 3 4 5 6 7 8 9. Okay, so for n is equals to 12 suffice for this, because for that we have value 479001600, which is less than 3600 to the power of 8. So that means this is good. Now 1 hour done. Yay. 1 hour, and then 1 day. In 1 day we have 24 36 to the power of 8. Okay, let me do 24 into 36. It is nothing but 864 into 10 to the power of 8. 1 2 3 4 5 6 7 8 9. Okay, so 13 factorial is less than that. I can check for 14 factorial. Let's see. Okay, 14 into 13 into 12 into 11 into 10 9 8 7 6 5 4 3. It is 8.7 10 to the power of 10. So definitely this does not suffice, and 13 does. So for 1 day we can process like 13 value. Now 1 day done. Nice. Okay, 1 month. 1 month has 30 days. And factorial, I'm gonna take 30 into 864 into 10 to the power of 8. Okay, let me do 864 into 30. 2592 into 10 to the power of 9. Actually, no, plus 11 12. Yeah, 14 factorial obviously does not suffice. So let's 14 factorial is less than that, but what if 15 factorial? Let me see. 15 into 14 into 13 into 12 into 11 into 10 into 9 into 8 into 7 into 6 into 5 into 4 into 3 into 2. It gave me answer which is good, which is there. Okay, sorry. Which is 1.3 into 10 to the power of 12, which is obviously less than this. Okay, that means 16 factorial could also be answered. Let's see. I mean, obviously not, but we have to prove it. So 16 factorial is 2 into 2 and 9 into 10 to the power of 13. Okay. So obviously which is greater than this thingy. So for 1 month, 15 is the correct thing. Now for 1 year. 1 year. In a year, we are going to consider days 365 into 864 into 10 to the power of 8. Let me multiply 365 into 864 into 10 to the power of 8. It is nothing but 3.15 to 10 to the power of 13. Okay, so 16 factorial looks less than that, and I'm very, very sure that 17 factorial won't be less. But like we have to check. So 17 into 16 into 15 into 14 into 13 into 12 into 11 into 10 into 3.5 into 10 to the power of 14. So obviously for 1 year, sorted value for n is nothing but 16. Okay. Now we gotta solve for a century. Okay, nice. Okay, let me just type the problem right down. That was in 8th one and factorial 1. We are solving for a century. Now n factorial should be less than 365 into 864 into 10 to the power of 8. Oh, 10 to the power of 10 cut then you can 100 either. And this also we had done it. Okay, first let 365. Okay, 365 into 864 into 10 to the power of 10 equals 3.15 into 10 to the power of 15. Awesome. We have 17 factorial, which is less than that. So 17 factorial is less than this value. But we gotta try for 18 factorial. Let us see what is 18 factorial equals to. 18, 17, 16, 15, 14, 13, 11, 10, 9, 8, 7, 6, 5. It is 6.4 into 10 to the power of 15, so it is definitely not less than n factorial, so that means the proper value for this is nothing but 70. Okay, so for n factorial, the values that can be processed within 1 second is 9, in 1 minute 11, in 1 hour we can process 12, in 1 day we can process 13, in 1 month we can process 15, and in 1 year we can process 16, and in a century we can process 17. So we have seen the input size which has decreased. I mean, it has decreased drastically with the last one. So yep, that's it for chapter number 1. Bye bye, meet you while solving chapter number 2. Ta-ta. Be happy and keep solving.